In this video, we connect linear transformations to matrices. We will see that a matrix is a convenient way of expressing the essential information about a linear transformation. First, a theorem. In a previous unit, we saw that the linear transformation applied to a linear combination of two vectors yields the same result as you get if you take the same linear combination of the transformed vectors. This theorem extends this to the linear combination of many vectors. It says that a linear transformation of a linear combination of n vectors is the same as that linear combination of the transformed vectors. We can write this more concisely with summation notation. Recall that any vector x can be written as a linear combination of the unit basis vectors where the coefficients equal the components in vector x. If y is the result of transforming x, then we can write this as L of the linear combination of the unit basis vectors, which we then know equals the linear combination of the transformed unit basis vectors. If we then label as A sub j the result of transforming the jth unit basis vector, then we see that the net effect of transforming x is the linear combination of the vectors A sub j, where the coefficients for the linear combination are the components of x. We can also write this as follows. This is huge. The linear combination is completely described by the n vectors A sub j, where A sub j is the vector that results from transforming the jth unit basis vector. L equals the sum of chi sub j times the vector A sub j. In other words, L is completely described by how it transforms the unit basis vectors. We now take the vectors A sub j and make them the columns of a two-dimensional array that we will call matrix A. Think of this simply as a convenient way of storing all information about the linear transformation L. Then, the ij element of this matrix equals the ith component of the vector A sub j. So, we now have an m by n matrix A that represents L. We can now write Ax as an alternative to writing L of x. But how is A times x computed? We're going to start calling this A times x. We know that Ax must have the same effect as evaluating L of x. And we know that L of x is the same as the linear combination of the vectors A sub j, where chi sub j is the jth component of x and A sub j is the transformed jth unit basis vector. We can then rewrite each of the vectors A sub j by exposing their individual components. But we know how to add scaled vectors together, leaving us with this result. Finally, we remember that scalar multiplication commutes. Now, remember from high school how to multiply a matrix times a vector. You get exactly the same result. So, our definition of Ax that makes it just an alternative for L of x yields the same definition for matrix vector multiplication as you have seen before in an algebra class in high school. Let's summarize. The action of a linear transformation is completely described by how it transforms the unit basis vectors. A linear transformation can be encoded in a 2D array. We call this array a matrix. Evaluating the linear transformation is the same as performing a matrix vector multiplication.